let us see how Riemann will probably integrate e to the x from 0 to 1. And of course, we will not be using the Fundamental Theorem of Calculus part 2, meaning we are not going to be finding an antiderivative for e to the x and then plugging 1, plugging 0, and subtract. I know the answer is e minus 1, but how do we do it without the Fundamental Theorem of Calculus part 2? In this case, we will give a limit of a Riemann sum a try. Check this out. We will interpret this as the area under the curve, and let me just write down all the steps for you guys. Let's say we have e to the x looks like this. And let's say here is 0 and here is 1. So here is the region that we want. What we will do first is look at this interval. We divide this into unequal parts. Since this is just 1 divided by n, each little part will be 1 over n. That's the first x value. The next x value will be 2 over n, and then 3 over n, and so on, so on, so on. Starting right here, you can pick 0 or you can pick 1 over n. Doesn't matter. I will use the right end point, meaning 1 over n here. Start right here, go up to the curve, and then draw a rectangle like so. And then we will find the area of this rectangle, which is the base 1 over n times the height, because we use this as the x value. Put it here, we get a y value, e to the 1 over n. And then do the same thing for the next one, and we will use this for the x value. Go up, create a rectangle. So the base is still 1 over n, but the height is now e to the 2 over n. And then just continue the same fashion, and then just keep on going. And perhaps we'll also write down the last one. 1 is the same as n over n. Go up, hit the curve, and then draw a rectangle like so. Base is still 1 over n, and the height is e to the n over n. So this right here represents the sum of n equal width rectangle under e to the x. And now, how many rectangles do we want? Well, we want to have as many as possible. We want infinity. So that way we can get the whole area. This is the time that we'll take the limit as n goes to infinity of this expression. So now, instead of looking at this integral, we'll be dealing with this limit. We'll do some algebra. Everybody has 1 over n, so factor that out. But you still have to keep them inside of the limit because n is approaching infinity for this limit. So 1 over n here, and then we will have e to the 1 over n plus e to the 2 over n, and so on, so on, so on, up to e to the n over n. This right here is actually really nice because this is just a geometric series, a finite version of it all. From here to here, you can see that take e to the 1 over n, multiply by e to the 1 over n, you get to e to the 2 over n because you can just add the exponent. And then in fact, to get to e to the 3 over n, you can do the same thing. So in fact, this is the geometric series with a common ratio r equal to 1 over n. Yeah, so, okay. Then how do we kind of put them together though? Well, here's the thing. Suppose we have r plus r squared plus dot 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 up to r to the nth power, which is this equation. First, we can factor out the r, and we get 1 plus r plus dot 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 up to r, 1 power less, right? This right here, in fact, we can factor it, well, it's right here. It's equal to 1 minus r to the n over 1 minus r. Why? Because this thing on the top can be factored as 1 minus r times 1 plus r squared, and so on, so on, so on, up to r to the n minus 1. You can just try multiply it out. 1 times this, negative r times all that. You can see all the middle terms will cancel. You just get 1 and then minus r to the nth power. So this is on the top. 1 minus r cancel, which is very nice. And this is how usually people present the formula, but I really like to have the r going first. So I will write this as r times r to the n minus 1 over r minus 1, because we can switch the order of subtraction on the top and on the bottom. Factoring out negative here, and then negative here, and then negative cancel, we get this. So using this, we will get the limit as n goes to infinity. We have 1 over n, and then here the r is 1 e to the 1 over n. We first have that right here, so just put that e to the 1 over n. And then we have r to the n, which is e to the 1 over n to the nth power minus 1 over r, which is that, and then minus 1. Now this is looking very nice, because first the 1 over n times n is just 1, doesn't matter, and we have the e minus 1, which is just a constant. So we can put that to the front of the limit. And then we have, check this out though. I'm actually going to do the limit of this part right here first. So that's the limit as n goes to infinity of e to the 1 over n, because this right here is just equal to 1. And then we look at the limit as n goes to infinity, this put it on the top over this right here on the bottom. And we can do this because the limit of a product is a product of limits if the limits exist. They do exist. So firstly, we have e minus 1 stays the same. Plugging infinity to here, 1 over infinity is 0. E to the 0 is just 1, so this is nice. And then this right here, in fact, it's also equal to 1. So the final answer is just equal to e minus 1. And we are done. Yes, and I know what you guys are thinking. Why is this equal to 1, right? Do we do L'Hopital's rule or not? Not so much, but here's the explanation. I will do a change of variable. 1 over n, same thing. So I will let t equal 1 over n. And because n is going to infinity, so t will go into 0 plus. We can look at this limit as t going to 0 plus, and then the top is just t, the bottom is e to the t minus 1. Now, check this out. I'm going to look at this as a limit as t going to 0 plus, and then I will do 1 over e to the t minus 1, and then over t, like this. Why? Because this right here, we can look at this as the limit of 1, which is just 1. So it's 1 over the limit as t going to 0 plus of e to the t minus 1 over t. And in fact, this right here could be the definition of the number e. Let e be the number so that the limit as h going to 0, and we use e for the base raised to the h power and then minus 1 over h. We want this right here to be exactly equal to 1. So this is just really by the definition of the number e. A definition, because there's also another version for it. So that is 1. That is e minus 1. We're done.